Good morning, Excel GO. What we're going to do today is we are going to learn about section 9.6, which is symmetry. And the two types of symmetry that we're going to investigate today is going to be line symmetry and rotational symmetry. Now to start this, we're going to do a warm-up. And this warm-up is going to review some of the information that we've learned previously in the beginning of the year. Now it says, find the coordinates of the image of A for each reflection. Now this is my pre-image A. And what I want to do is now find the image after it has been reflected over the given line. So if I take a look at this, that line y equals x. We learned that if I had a point x, y, and I reflected it over the line, it would change it to the point yx. So that point now, 3, negative 3, 8, a prime, because we use prime to identify the image, would then be 8, negative 3. Now, if I now took that original point, negative 3, and I reflected over the x-axis, my xy value would change by, if you reflect something over the x-axis, your y value changes. So your x-axis stays this, your x value stays the same, and your y value becomes its opposite. So therefore, a prime would be negative 3, negative 8. Okay, so if I reflected in C over the line y equals negative x, if I reflected over the line y equals negative x, the x and y switch places and signs. So this would become negative y comma negative x. So if I look at this, now my a prime for this reflection would be negative 8 comma positive 3. And the last reflection we're going to review is the y-axis. If I took that point, xy, and I reflected it over the y-axis, the x value would change and the y value would stay the same. So my a prime here would be 3, 8. All right? Now the first side of this worksheet, we are going to be talking about line symmetry and what line symmetry is. Another term you might hear is reflection symmetry. They are the same. So what is line symmetry? A figure in a plane has line symmetry. So a figure in a plane has line symmetry if the figure can be mapped onto itself. So that's when we can have line symmetry, if we can map the figure onto itself. Now, when we look at the line of symmetry, what I classify as the line of symmetry will be the line of reflection is the line of symmetry. So let's write that down. The line of reflection is the line of symmetry. All right, guys? Okay, so let me show you an example, and a basic example. Now, if I had pretend that I drew a perfect shaped heart. If I had that perfect heart, it would have one line of symmetry. If I drew a line right through the heart, like that, I drew this line here, right here, this line, this would be my line of symmetry. Okay? That would be my line of symmetry. And if I looked at it, the heart has what we call line symmetry because I can fold it down the middle and one half of it would lie right on top of the other half. So I can write the heart has line symmetry. Excellent. Now what we're going to do is you can have multiple lines of symmetry. In this example, this heart only had one line of symmetry and it was right in the middle. It divided the heart into two even parts where if I folded the one side of the heart onto the other, it would map right on top of itself. So that was an example of something with one line of symmetry. However, you can have multiple lines of symmetry. So in this case, if I take a look at my line of symmetry, lines of symmetry, so we have plural because we have plural here because we can have more. In an example like this, I have a hexagon. It's not regular because these two sides are longer than the other two. But if I look at this, there are two lines of symmetry that I can draw. I can draw a horizontal line of symmetry. If I folded it on the horizontal line, the top of the hexagon would fall right on top of the bottom, so it would map onto himself. And then I can also draw a second line of symmetry right in the middle of the two, top and bottom here. And if I folded the hexagon on that line, it would also map onto itself. The one half would map onto the other half. So this would have two lines of symmetry. All right. Now my next one's slightly different. This was not a regular hexagon. This is a regular hexagon. So when you take a look at a regular hexagon, it will have more than two lines of symmetry. It'll have the same two that we just did in the other one that wasn't regular, but it was still equal angular. So here I have the two that I had in the other one. However, because it was regular, I have more. I can now actually rotate around this figure and I can find multiple lines of symmetry. So I can divide each side in the one that's parallel to it right in half to draw a line of symmetry, and then I can connect two vertices that split it in half to draw lines of symmetry. So if I take a look at this, how many lines of symmetry do I actually have? And it's 1, 2, 3, 4, 5, 6. I have 6 lines of symmetry. Now, if I look at example C again is a hexagon, but in this case it is not. This one, the first one was equiangular, not equilateral. This was both equiangular and equilateral, so it was able to have 6. The one that was just equiangular, but two sides differed in size, I was able to have 2. This is not equilateral or equiangular, but it still has one line of symmetry, this hexagon. All right, so this would have one line of symmetry. So all right. Now let's take a look here. How many lines of symmetry does the object appear to have? So again, we can have lines of symmetry in objects in nature, and these are a couple of examples. Now if I take a look at this, I have a flower. But if I keep on drawing, I can draw this flower right in half, and I can see I have 2 petals on this side and 2 petals on that side, that if I folded it on that line, it would map onto itself. Now how many more cases do I have there? Well, I have that one. I can draw it this way too. That's 1. This is a second line. Would be 2. Is there any other way I can draw this? Well, I can cut it in half this way. The top would map onto the bottom. So that's 3. And then I can cut it in half right here. And that would be 4. So this would have 4 lines of symmetry. All right. Now, in part B, the starfish would be slightly different because the starfish, I can break it up by connecting a vertice, the tip of the starfish to like right between 2 legs. So if I drew this, that would be 1. That would be 1 line of symmetry. I can map one side if I folded it onto itself. But that pattern will continue. If I go around my starfish, that would be 1. This would be 2. And I do this vertice, this would be 3. I got 3 lines of symmetry. Do another one here. This would be 4. And my last line of symmetry would be through the last vertex that I didn't use yet. And this would be 5. I would have 5 lines of symmetry. Now my last one, right here. This one I would just have 1. It would be symmetric right down the middle. So I would have 1 line of symmetry. All right, guys. Now, if we take a look at this, these are a couple examples. These were all hexagons, and here's some real life examples of where we can see symmetry. Now this says draw a hexagon with no lines of symmetry. So up here we had a hexagon with 2 lines of symmetry, 6 lines of symmetry, and 1 line of symmetry. None, I just have to make sure that it cannot be divided. So for an example of something that has no lines of symmetry, it could be any hexagon shape. So if I look at this, I'm going to do 1, 2, 3, 4, 5, 6. So I have a 6-sided figure, and this 6-sided figure has no lines of symmetry. Okay, guys, let's flip it over now. Let's finish our notes on the back. Now, on the back, we start talking about what we call rotational symmetry. And rotational symmetry is slightly different, obviously, because instead of folding it over a line of symmetry or reflection line, what we're going to be is we're going to be rotating the figure. So a figure can be mapped onto itself by a rotation of 180 degrees or less. So rotational symmetry is a figure can be mapped onto itself by a rotation of 180 degrees or less. I want to make a note. It could go clockwise or counterclockwise. That's why we don't say a 360-degree rotation. We're going to do it based on direction and degrees. So you can say it's 60 degrees counterclockwise, 60 degrees clockwise. You can rewrite it like that to help us out. Sometimes I might just say it's a 180-degree rotation. That doesn't matter which direction I'm going in. And sometimes you can just write 60 because it might be a 60-degree rotation both clockwise and counterclockwise. Now, if we take a look at this, it says about 180 degrees or less. It could be clockwise or counterclockwise, and it's rotated, in this case, or less. It's going to be about the center of the figure. All right? And that's when we know it has rotational symmetry. All right? Now, the center of symmetry is that point. So the center of the figure is the center of symmetry. All right, guys, the center of symmetry is that center of that figure. All right? So now what we're going to do is let me show you how this works down here. Does your figure have rotational symmetry? If so, describe any rotation that maps the figure onto itself. You need to pick a point. So I'm going to pick a point. Always pick a point. Pick a starting point. All right, guys? And we're going to look if I can rotate it so that it lands on another point by itself. Now, if I'm going to compare it to vertices, if I put it here, it can't land there because this is an acute angle and this is an obtuse angle. It wouldn't map up to itself. But if I did a rotation like this, if I took this point and rotated around the center, this is my center of rotation. If I rotated that figure around the center, my blue dot would land right on top of there and it would map onto itself. I'd have the same exact quadrilateral. Because of this parallelogram, I'd have the same exact parallelogram, I would have rotational symmetry. Now you want to ask yourself, what is the rotational symmetry? Well, we want to think of it as an angle measurement. If I'm rotating it from here and I'm landing right there, that forms a straight angle. So that would be a 180-degree rotation. And the direction doesn't matter because no matter which way I did it, it would be a 180-degree rotation. So you would say this has a 180-degree rotational symmetry. All right. Now our next figure is a regular octagon. And again, you have to start with a point. And this is a special case. Anytime you have a regular octagon or a regular figure, every angle is the same and every side length is the same. So pretty much if you can take that one vertice and land it on any other vertice, it will have symmetry. It will map onto itself. So if you look at this, I can rotate to this one and it would work. I could rotate to that one, it would work. I could rotate to this one, it would work. And I could rotate to this one. And I'm going to stop here. I'm stopping here because I notice that if I draw these two, here's my center of rotation. If I draw this line, that would be 180 degrees. So remember, we said that the rotational symmetry, we're looking at it in terms of 180 degrees or less. So this is 180 degrees. I know it has 180 degree rotational symmetry, but it also has a couple others that are less than that. Well, this is a regular octagon. Break it up. I can draw these little triangles. And I have 1, 2, 3, 4 triangles. 4 triangles that have to add up to 180 degrees. So if you think about that, if these 4 triangles have to add up to 180 degrees, how do I find the rotation from here to here to here to here? Well, I'm going to think, if I take 180 divided by 4, 45. They're going to increase by 45 degrees. So this first rotation will be 45 degrees. The next one would be another 45, which would make it a 90-degree rotation. The next one would be another 45, which would make it a 135-degree rotation. And the last one would be our 180 degrees. So I would have 45, 90, 135, 180, all rotational symmetry. Now the trapezoid, again, you're trying to map it onto itself. I pick that point. I look at that center. Remember, it has to be through the center. Can I rotate it around the center? If I rotate it here, I'm manipulating it. But wait, this side is smaller than this side. So if I rotate it, nothing is ever going to map onto itself until I get back to my original point. If that occurs, and remember, it has to be 180 degrees or less, we have no rotational symmetry. Okay, guys, let's take a look at our next one. This rhombus. Again, pick a point. It doesn't matter. If I take this point, I want to try to rotate it onto other points. Now, if I can't, this is an obtuse angle. If I rotate it here, this is not an obtuse angle. It would not map onto itself. If I rotate it here, around my center, if I turn that around my center, then this point would line with this point would line here, and I would have rotational symmetry. If I look at that, that would form that straight line. If it connects the center and the opposite side, that would be 180 degree rotational symmetry. Now let's look at our next one. We got our center of rotation. Now think about this. This is a star. So if I think about this point right here that I'm picking, the point, I pick one point and I want it to rotate. Well, it would have to hit another point in the star. If it lined up there, if I turned it there, it would line up. It would map onto itself. If I turned it here, it would map onto itself. I can stop there because I notice if I connect this, this forms a straight angle, which would be 180 degree rotational symmetry. So now I have one point in between. Well, that means I would take that, if I remember, we look at it, we'd take that, divide it into 2. This is 180. Half of 180 is 90. So I would have 90 degrees and 180 degrees rotational symmetry. And a right triangle. Again, if I did that same thing, it wouldn't work. Because look at, would that ever map onto any other angle in this triangle? Absolutely not. If this is the right triangle, that's the only possible 90 degree angle. So this has no rotational symmetry. All right. Now down here it says identify the symmetry and rotational symmetry of the equilateral triangle at the right. Equilateral. So we have 3 congruent angles, 3 congruent sides, and we want to see what the symmetry is. So we're looking here, it's asking about for line and rotational. Well, if I think of line, how many line symmetries? I would have what? 1, 2, 3. From every vertex to every midpoint of the opposite side, I can draw a line of symmetry. So I have 3 lines of symmetry. So I can eliminate C and D. Now I'm looking at rotational. Now let's think of this. I start here. I can't do a 180 if I start there. The only time I could rotate onto itself is if I hit the next vertice, which should be right here. It's not 180 because I didn't hit over here. Now how do I determine, is it 60 or 120? Well, let's think about this. If I move this all the way onto itself, that would be a 360 degree. Each one of these vertices is breaking that 360 degrees into 3 parts. So if I think about it, I can rotate here, from here to here, it could rotate there, from here to here, it could rotate there. So I have 3 rotations that add up to 360. So I'd take 360 divided by 3, and that is where you're getting your 120. So you have 3 lines of symmetry and 120 degree rotational symmetry. Now they're asking, the last fact it's asking me is, what if it was a non-equilateral isosceles triangle? Well, let's think about this. If it's non-equilateral isosceles, right? I know these two are congruent, and those two are congruent, but that's it. What would I have? Well, I can't rotate my angles because this angle cannot lie on top of another angle. So it has no rotational symmetry. Does it have line symmetry? Yes, it would have one line of symmetry. And that line of symmetry would go from the vertex angle all the way to the midpoint of the base. So we'd have one line of symmetry. All right. I hope you got your notes down today. If you have any questions, please come to office hours. They're on Google Meet. I will send out an announcement prior to office hours with the link to Google Meet. In addition, your homework is posted under the assignment. When you complete it, please upload it to this assignment today. If you get it complete, if you don't complete it today, but complete it by tomorrow, that is fine. Just make sure you upload it to today's assignment. All right, guys, I will hopefully see you at the Google Meet if you have any questions. Otherwise, have a great day. Bye.